So we're suspended, and it's looking like we're suspended from above. And so once again, I'd like to sort of divvy up my colours. Black part represents natural length. Green part represents the extension at equilibrium. Okay, and it says that this is a point Q. Hands at equilibrium at point R. And it's called P, but they decided to call the position at equilibrium R. Okay, so that's alright. And it has a mass of half a kilogram, so weight is mg, which is, I'm thinking straight away to put everything doesn't have gravity in terms of it, so I'm just going to get rid of the 9.8 immediately. So it's going to be 4.9 newtons straight downwards, alright? So we'll go for our 4.9 straight downwards. Alright. Next thing we're going to do is we're going to find the tension in the string. And we'll call this distance D. Now, if you remember from the last question, tension is K times L minus L0. That can also be written as what, lads? K times extension, alright? It's the same thing. And then therefore, what's our K value? 24.5. 24.5 multiplied by the extension coefficient. Oh, sorry, by the extension. We've claimed that the extension is D, haven't we? And that in turn equals 4.9. And I believe we're just going to divide. We're going to divide 4.9 by 24.5, and we're going to get a D value of 0.2. Now remember, the natural length was 0.65, wasn't it? So the black length was 0.65, and then 0.65 plus 0.2 gives us our 0.85 meters, which is a lovely way to start the question. Okay, very easy part one. We will take that every time. Okay, part two. Once all this is gone. Part two, our position R is our equilibrium position. So I'm going to mark off the equilibrium position with a horizontal line, like so. And what we're going to do is we're going to extend our particle a bit further down. So we knew that D was 0.2. And now you're going to have a new. Now once again, please don't just remember you're talking about a generic distance x, anything below equilibrium. There we go. And that is what we call that, lads. We will call this, oh yeah, that's 4.9 n divided by particle. That's particle P. That's your equilibrium position R, and this is our generic distance x. Now, this time there's a force, net force moving upwards. Force equals ma. You're guaranteed that the net force is moving upwards because you've extended it too far down, and that means you're going to do your weight, which is going down, minus your tension going up, where tension is the bigger number. Mass is a half, so it's a half A, equals your 4.9 newtons. Now once again, we can do minus K times extension. It's quite obvious what the extension is, isn't it? Can anybody read what the extension is from a diagram? What else though? It's the extension above the natural length. So the black line represents the natural length. The green line represents the extension at equilibrium. and the red one represents the new extension below equilibrium. So what is your total extension then? Yeah, it's your x plus your 0.2. Okay? So a half a equals 4.9, don't mind the Newton sign. Now, what's a 24.5? X, just x plus 0.2, because I'm just doing extension. I'm not bothering with L minus L0 this time. You can do that if you want. What has to happen? What's guaranteed to happen? Those two 4.9s are going to cancel, aren't they? They will. And you'll end up with a half a equals minus 24.5x. And then you'll end up with a equals minus 49 over x. And that, my friends, is an omega value of 7. So you can see what the marking scheme says. Therefore, SHM, and I like to go a step further with omega equal to 7, because it's minus omega squared x. And what's the amplitude of its motion? 0.3. Okay, I'm going to stop here for a sec. Where is the maximum speed? Does anybody remember how simple harmonic motion works? At the amplitude, its velocity is 0 and it undergoes its maximum acceleration. When it finishes off the red zone and hits equilibrium, equilibrium means net force is 0, hence acceleration is 0. This means that the point R is the position of your maximum speed. Cool with that? Anything above that, what's happening? You're being decelerated back towards the equilibrium position. So we take out our good old friend phi squared equals omega squared a squared minus x squared. And what did we figure out? That the displacement has to be 0, as in you're actually at the equilibrium position. So therefore phi squared equals 7 squared, which is 49. What's our amplitude again? 0.3 squared, and our x value? 0. And then the answer is 2.1, but you can figure that out yourselves if you want. 49 multiplied by 0.09. Root your answer. Yeah, phi is 2.1. Everybody cool with that? Yeah.